Let's try to do this problem. First, we'll read the problem carefully. It says, what is the electric field at the lower right-hand corner of the square shown below? So here's the place they're talking about, the lower right-hand corner. And we want to find the electric field at this point, which is created by these three charges. There's a plus Q here, minus 2Q on this corner, and a plus Q on this corner. Now each one produces its own electric field, and using what's called the superposition principle, you can just add them. Now the electric field is a vector, so you have to add them vectorially or by components, but at the end you'll get an expression that shows the total electric field at this point. Okay, so let's get started. We will do part A, which is to find the electric field. Now everything is in terms of variables, so we're gonna, well, there are no numbers, so the best thing is to first label these charges. So why don't I call this 1, this 2, and then this 3. Okay, so let's focus on 1. If you want to know what the electric field is from 1, remember the rule is electric field lines go away from a positive charge, and for negative charges, the electric field lines go into it or towards it. So if we were to draw the point charge for this one, the electric field would go away like this in every direction, right? So if we were interested in finding the electric field at this point, it'll be going up and to the right. If the point was, we were interested here, it would go down and to the left. What we're interested is here. This, what the electric field due to this charge is at this point. So in that case, it's very clear that at this point, it's just going down. And we'll label that as E1. Now, the electric field due to charge 2 is going to look different because it's negative. The electric field lines will go towards the charge like this in every direction, towards the charge. And we are interested in what this field is at this point right here. So at this point, it's going to go towards the negative charge and point up at 45 degrees, and we'll call that E2. For the third charge, same idea. It's a positive charge. The electric field lines will be radiating away from the charge, right? Everywhere. And at this point that we're interested in, it will be going towards, completely towards the right. Now, never mind the size of these arrows. I don't have them correct. They should be different sizes. So this is going to be that way. Now, if we do want to worry about the sizes, the distances and the charge determine the size. So these charge 1 and 3 have the same charge value, and they're the same distance from this point, so they should have the same size. It's different direction, but the same size. Now, the electric field E2 due to the minus 2Q charge is, in terms of magnitude, stronger because it has a higher charge value, but it's also further away. So it's not clear, at least initially, what this. So we're not going to worry about the size. We'll let the math figure this one out. Okay. So our job now is to find the total electric field by adding these three fields up, E1 plus E2 plus E3. And we're gonna, these are all vectors, so you have to put the vector arrows on top of them, or else they're not vectors. And to do this now, we have to add each component separately. Then we'll sum them, we'll put them in, okay? So we can write this E total as E1x plus E2x plus E3x times I hat, that's in the x direction, plus E1y plus E2y plus E3y times j hat. Okay, so let's figure this out. E1x x plus E2x plus E3x. So I'm just going to look at the x components now. What is E1x? Well, you can see that E1x, there is no x components, all in the negative, all in the y direction. So this is going to be equal to 0. E1x is equal to 0. What about E2x? Well, E2x does have an x component. Is the x component, if you want to zoom in here, will be equal to, this is what it looks like, E2x. Remember, you draw a little triangle, and then the y component will be that. So that'll be E2x, and that'll be E2y. Now E2x is pointing in the negative, or to the left in negative direction, so it'll have a minus sign. So minus, right? And we're gonna minus times the magnitude of E2 times whether it's a sine or cosine. Okay, now what do we mean? Well, if this was right here, theta, that would be the theta we're talking about. Of course, this is a 45-degree triangle, so we'll call this 45 degrees. Not a triangle, sorry. This is a square, so if this angle will be 45 degrees. And E2x is adjacent to this angle, so we're interested in cosine. Cosine 45 degrees. Okay, so right now we have E2x. E2 is the magnitude. The minus sign tells you it's going to the left. E2 is the magnitude, and then the cosine 45 gives you the x component of that magnitude. Okay. Now last is E3x. E3x, as you can see here, is completely in the x direction from here. So there's no y component, and it's positive. So what we're just going to do is put plus E3, the magnitude. Okay. Now we're going to put in what the magnitudes E2 and E3 are. This is where we use Coulomb's law involving K's and Q's. So we have equals minus K, and we're talking about the Q2 charge, which is over here, and this has charge minus 2Q. Now we already accounted for the fact that it's a minus, right? That's why it's going towards up and towards the left. So we don't want to double count. We're just going to put down the fact that it's 2Q. Okay. Again, the minus sign has already been taken into account here. So we don't want to put another minus sign. That'll be a double negative and cause problems. So that's the formula. Remember the formula for Coulomb's law is AQ over R squared. That's the Coulomb field for a point charge. And we're going to put K here, the charge of Q2, and then the distance from the second charge all the way to that corner. Now, what is this distance? We're talking this distance here to here. It's not A, okay? It's not A. If you remember, for a square, a diagonal of a right triangle at 45 degrees, the diagonal is A root 2. So this distance here is actually A root 2 going from one corner to the other. And that's what we'll put down into this denominator. A root 2, the whole thing squared. And then cosine 45 degrees. And then for E3, the charge is just positive Q. So KQ over the distance squared, which in this case would be A squared. Okay, we're going to continue evaluating the expression. So I'm going to take the 2 out. So I have minus 2KQ. And then I'm going to square the bottom. When I square the bottom, I have root 2 becomes 2. And then A becomes A squared. Now, what's cosine of 45? Cosine of 45, if you remember your right triangle, reference triangle, it is 1, 1, root 2, 45. And so cosine is adjacent over hypotenuse. So cosine 45 degrees is 1 over root 2. Instead of putting in the calculator and getting a decimal, we want something that's a nice expression. So we'll put 1 over root 2 down here, like that, for cosine 45. Cosine 45 is 1 over root 2. And then we'll copy the next term, KQ over A squared. And we continue with our simplifications. These 2's will cancel, and you have root 2 on the bottom. Both terms have KQ over A squared. So whenever you see that, you can factor it out to simplify. So if I put KQ over A squared, I factor that out, pull that out, I'll have what's left is, this is minus 1 over root 2 will be left, and then this will be 1 that's left on this side. I'm just going to make it neater, so minus 1 over root 2. I switched places there just to make it look nicer. Okay, so that's the total x component due to the 3 charges. Now we want to work on this, the total y component, and it's going to be very similar. So we want to know what E1y plus E2y plus E3y equals. So E1y, so you can see E1 has no x components, all of it's in the y, and it's going down, so it's negative. So it's going to be negative times E1, the magnitude. Okay. Next, E2 does have a x component, so it's not completely in the y, but it's going, the y component we've shown here already, it's going up, so it's going to be positive E2y. And then last is E3. Now E3 has no y components, completely in the x, so we'll just put a 0 there for it. Okay, now just like before, we'll write down for E2, it's going to be equal to a hypotenuse times their sine or cosine. Okay, so in this case, it'll be, since it's E2y is opposite 45, it'll be sine. E2 sine of 45 degrees. Okay, now we're ready to put in the Coulomb's law. Negative sign, K, and then the charge of E1 E1 is positive Q, so we'll put Q and then over the distance to the E1, which is A squared. So that's E1. Next, we want the magnitude E2. E2 is negative 2Q, but we don't want to count this as a negative anymore. We already took into account the minus sign from these directions. So it's just positive 2Q. Okay, positive 2Q over the distance from E2 to that point, which again is going to be A root 2, and then we square that, times sine 45 degrees. Okay, if I continue evaluating this, I get minus KQ over A squared, plus 2KQ, take it out of the parentheses there, I square the bottom, which I'll get 2A squared, and then sine 45, just like before, it's sine 45 equals cosine 45, so it's be 1 over root 2. And we continue along. These two terms cancel like that. And if you want to write it more nicely, we take out factors that are the same. In this case, it's KQ over A squared. And then write 1 over root 2 minus 1. Right? Because this is the minus 1, and then this is 1 over root 2. And that's what I have there. Okay? Okay, so now we're ready to see what this looks like, the total electric field looks like. We'll put E total vector. Remember, it's equal to E total X, which is just found, times I hat, plus E total Y times J hat. And if I put it in the expression above, we have KQ over A squared, 1 minus 1 over root 2 times I hat, plus KQ over A squared, 1 over root 2 minus 1 J hat. Now you notice that these two terms are actually just opposite of each other, right? Because if I put a minus sign here, this becomes 1 minus 1 over root 2, which is the negative of this. So we can actually simplify it a little bit more by writing out KQ over A squared, pulling out this, and then we'll have I hat minus J hat, right? Because the second term, the J hat term, is minus the other. So this is the most simplified form of this electric field. Now, we know that this expression is positive, right? Everything is assumed positive. This expression is positive because 1 over root 2 is 0.7. 1 minus 0.7 is a positive number. And then what we have is two components, one going to the I direction and the other going to the negative direction. So if we were to draw this E total field, it's that they both have the same size magnitude, 1 and 1, so they're 45 degrees. And it'll go down like this, right? Because one is going to the right and the other is going down to the minus. So this would be what E total will look like. It'll be going down and to the right. The last part of the question is part B. And it says, what force on charge Q placed at that point. What is the force on a charge Q placed at that point? Well, that is a very simple thing to do. What we're going to do is use the equation to go from force to electric field. So in this case, part B, to know what the force is, we're just going to take the charge Q. That's what they said. If you're going to put a charge Q at that point, then you times the total electric field. So it's a very simple step. You're just going to take the expression above and multiply by Q again. So you have KQ squared over A squared, 1 minus 1 over root 2, I hat minus, I hat minus J hat. There. Those will be the two answers of this problem. Let me just go ahead and box these. They look nice. That would be the final answer right there.